Good morning, ladies and gentlemen. I am currently in the process of trying to drastically change my sleep schedule. So I was up for 24 hours yesterday. I'll be up for 26 hours today. And I've been up for 7.5 hours now. So I have a long way to go. So I figured I would make this nice little complex analysis lecture since it also relates to probably one of my most, no, the most memorable math problem I've ever done for homework. So the structure of this will be that the end goal is to evaluate the integral I'm going to show you. And of course, that'll require a lot of buildup. So I will essentially skim through about 2.5 months of complex analysis. And I'll say something briefly about complex analysis. So what complex analysis is just the study of complex numbers, right? Like I and the plane that you can get with them. And there's very surprisingly a huge amount of things you can do and a lot of very nice results that come out of it, particularly with integration and with functional analysis. And that comes up in uh, applications a lot. I mean, it's big in physics, like a lot of electromagnetism and uh, yeah, I guess quantum mechanics revolves somewhat around things that you get from complex analysis. And the course itself, usually colleges have an undergraduate course and a graduate level course where the undergrad course doesn't get too deeply into the actual really rigorous analysis side of it. It just sticks to what I like to think of as spicy Calc 3. So it's really fun. It's my favorite math class I've taken, at least the graduate level version. The undergrad went a little slow. Um, and I'll show you why. Because you get to do problems that are just fun, like with real analysis. The problems can be very gritty and long and tedious and definition and theorem heavy. And with uh, topology, I'm just not a fan of topology. And algebra is just painful for lots of reasons that I'm not going to go into. I can make a whole nother video on that. But this seems like a good balance where there's still a lot of fun stuff going on and you can still visualize it because you can sketch out the complex plane. We're going to sketch some things out. It's just a nice balance. So I'm going to give you some background and help walk you through how I solved this integral. So here you go. So the integral is this. It is the integral from negative infinity to infinity of x cubed over x squared plus 1 quantity squared times e to the negative 2 pi I x c dx, where c is some fixed real number. It could be positive, could be negative, could be 0, whatever, right? And the bounds here, this is an improper integral. So technically what this means is that you have a limit as like a goes to infinity of negative infinity, negative a to a. So before we get into all the complex analysis stuff, I'll point out that since we're going to break this into cases, depending on what c is, if we do the case c equals 0 first, then the integral turns into this. And notice I'm doing the proper thing for this improper integral. X cubed over x squared plus 1 squared dx. Because when c is 0, this exponent is 0, so this whole thing is just 1, so it doesn't really play a role. But then this, if we think of it in terms of a, is just 0. And why? Because this is an odd function, right? Because the denominator is even, the numerator is odd. And if you're integrating an odd function from negative a to a, then it's always 0. So that's just 0. So there's case 1. Next case will be c equals, or c is less than 0. But that is insanely trickier. So we will now begin the complex analysis lecture. All right, so we'll start here. And there are many components that we'll require for the process of solving this. So we're going to work through them. So first, we have the definition of what a residue is. So, and there are lots of things in here that you're not going to know what they are, but I'm going to talk through them. So I'll introduce this first. So let U be an open set in the complex plane. Open just means if you have any point inside of the set, then you can draw a little ball or a little circle around it that is also contained inside the set, which essentially means like it's a set, but it doesn't contain its boundary. So it's like a dotted line boundary, sort of. So let it be an open set and let U or F, the function F, which maps U except for this point. So this denotes the domain is U except for this point Z naught. It's a complex value function, be a holomorphic function, and I'll introduce what that is, so that there exists some positive number R such that this represents a ball of radius R around, it should be Z naught actually, ball of radius R. So that just means if you have Z naught right here, then it's all these points in this disk with radius R, excluding the point Z naught, or actually including the point Z naught, excuse me, and excluding the boundary, right? And that'll come up a lot. So that there's this, what's called a ball, and a sequence, AN, which actually is not indexed by natural numbers, it's indexed by all the integers. So as we can see here, it goes from negative infinity to infinity, such that the function is equal to this sum from negative infinity to infinity of a spin times z minus z naught to the n on this. So this is what's called an annulus. So it's a lot like a ball, except it has an inner radius also. So in this case, the inner radius is 0, which essentially just means you don't include the inner point. So you don't include z naught. So it's like this, but without z naught. But in general, like if I were to give you an annulus like A with a small radius R and big radius R, it would be like this. So it's like a donut where this is the small radius, this is the big radius. So that's called an annulus, right? So, okay, F is equal to this weird looking series, and we'll get to this too. Summing a series from negative infinity to infinity is definitely something new. And it only converges on this annulus. So the residue, this is the important thing, of this function at this point z naught is the coefficient a negative 1. So it's the n equals negative 1 coefficient from this series of, yeah, we denote this by the residue at res at z equals z naught of f. So now we'll get into what all these things mean. So first, holomorphicity. So in complex numbers, you still have the notion of differentiability, of course, because that's extremely important. So you say a function defined on a set U is differentiable at a point if this familiar limit exists. So the interesting thing, though, is H is a complex number. So rather than in like single variable calculus or even in multivariable calculus, where H either approaches from the negative side or the positive side of 0, it can approach from anywhere. So in the complex plane, this is 0. H could go in like this, could go in like that, could go in like that. So it gets a little screwy. And I'm not going to get into the nitty gritty of that. But that's something to note. It's a new thing. So when the limit exists, we call that the derivative, and we denote it by f prime still. So a function is differentiable if it's differentiable at each point, which is the same way you define derivatives in normal calculus. So now, if we have a function on the set U, it is called holomorphic if the function is differentiable on U and the derivative is continuous. So holomorphicity turns out to be a very nice property. For example, I mean, if it's differentiable, then it actually turns out it's already continuous. So this is actually unnecessary to put. But also, if it's differentiable once, then it's differentiable infinitely many times. So it's what's called a smooth function, which is not relevant here. Actually, it will be relevant later. So we'll get to that. So holomorphicity, a very nice property for functions. Pretty much every function in complex analysis you care about is holomorphic to some degree. So a quick sidebar, and this is actually not relevant, but it's important to note. So a function on a set U is called analytic, different term. If for each point in that set U, there's some radius r and some sequence such as the series, the normal looking series, n equals 0 to infinity of a sub n times z minus z naught to the n converges everywhere in that ball and is such that the function equals it. So it's very similar to Taylor series. I mean, this isn't exactly a Taylor series, but it's saying that the function on some ball is equal to a power series, which is a huge concept in calculus, being a function being equal to a power series. And it turns out that every function that is analytic is also holomorphic, which makes sense because if the function is equal to the series, this is always differentiable. So if it's analytic, it's holomorphic. But also, if it's holomorphic, then it's analytic. And we'll get to that. So every function that is differentiable and has a continuous derivative can be written by a power series on certain disks. And exactly where you can write these power series, like on which disks it works, is a bit tricky. And this is actually something that pops up in calculus, but you don't really know it. Like, for example, the function inverse tangent of x. I don't remember the Taylor series off the top of my head, but the Taylor series actually doesn't converge everywhere. Like, even though the function looks like this, right? The Taylor series only converges roughly right on this interval, not everywhere. And that actually is because if you look at this function, but you generalize it to the complex plane, there are problems that show up where you can't get a disk big enough, which I won't go into. But this notion is important. So we continue on. So now let's get to that weird looking series that we talked about. So, okay, take a sequence of complex numbers where that's indexed over the integers rather than just the natural numbers, which is fine. So it's just a collection of numbers that happen to be labeled by integers. And you pick a point, complex number z, then that should be z naught. Then this series that we wrote down earlier, we'll now investigate it. So it converges, like the notion of convergence for this is if the series, when we just restrict to the natural number terms, like n equals 0 to infinity, converges, and all of the negative terms, which we write like this, starting at 1 to infinity, but we just denote negative n. If both of these converge, then that'll converge, right? So this is actually not that useful, but it converges absolutely if you just throw absolute, actually they're not called absolute value signs. In complex analysis, they're called moduli, or the modulus, because this is actually calculating the distance from the origin. Right, so the modulus of, say, a number up here is whatever that length is, which is really how absolute value works too. It's just on one dimension. And the series converges uniformly, which is complex, or it's a complicated analysis term, which isn't too important. Converges uniformly if each of these like sub-series converge uniformly, similar to how this converges if both of these converge. So now we can get to this. By this series, we mean the sum of that series, just the non-negative terms, and the negative terms, where this is, as we wrote up here, just the sum of all the negative terms. So we literally are summing in two directions sort of at once. So we call that series a Lorentz series. So Lorentz series are extremely important because they're really a generalization of Taylor series, which can actually be calculated in more ways than Taylor series can, but usually they're calculated in a similar way, though we won't actually talk about how they're calculated because it's not super relevant. A specific part of it we will, but so, and recall that the residue was just this -1 term of a Lorentz series. So the residue for a function on a specific annulus is that coefficient. So if we continue on, now we have this theorem that really tells us how holomorphic functions and Lorentz series go together. So suppose you have a function on an annulus with little radius r and big radius r, which is holomorphic. And this is just saying we pick the radii and the point at which it's centered. Then there exist two holomorphic functions defined, one of which on this ball. So if we sketch down here, our annulus, this is where the function is defined. So you have big R and little r. So G1 is defined inside the big circle, but the whole thing, it's not an annulus, it's a disk. And G2, when you write this, it's the complex numbers except for the, this is the closure of the small circle. This just denotes closure, which means you include the boundary. So essentially it's everything outside this dotted line. So G2 is defined inside this dotted line. G1 is defined inside this dotted line. G2 is defined outside this dotted line. So they're both defined on the annulus. So then F is equal to G1 and G2. And this just means like there exists some G1 and G2 with this property such that this is true. And moreover, you can write power series for each G1 and G2 because they are defined on disks. And I'll make a note on that when I come back. But there exists, you can then write this Lorentz series, which converges, well, this actually is not important. So we call this the Lorentz series, and the place where this AN comes from, right? So for the n greater than or equal to 0 comes from the series power series for G1, right? And then the AN for n is less than or equal to 0 comes from if we take G2 and so you can write it like this. The power series of 1 over G2 minus Z0, because this point is Z0. So essentially what this is also an holomorphic function, which is defined inside this disk. Because the inverse of a holomorphic function is holomorphic, and there's a bit of subtlety to that, but don't worry about it. So this is defined on a disk, so we can write a power series. And then when we invert it, really what happens is we just invert each of the terms. It's a little bit more tricky than that, but these negative terms of the Lorentz series come from the inverse of G2. And this isn't hugely important either. But this is what we need to know about Lorentz series. So now we can look at exactly what Lorentz series can tell us. So suppose we have a function defined on some open set except for some point z0 with a Lorentz series on the annulus, which is just a disk missing z0, right? Whenever the inner radius is 0, you're only excluding this one point. So F has a removable singularity, and F is holomorphic, of course. So it has a removable singularity, which, if you'll recall, it's the same idea from basic calculus, or actually before calculus, where you could just take the limit of the function as you get really close to, say, z0, and it would be a finite limit. So you could just define one point there, and it would now not have any problems. So it has a removable singularity at that point, if and only if an is equal to 0 for each negative n, which essentially says that this is just a power series, a normal power series, because all the negative terms are 0, so it just turns into n equals 0 to infinity. Which makes sense, right? Because there's no real like mathematical problems with a removable singularity. It looks normal, so to speak. So it's fine. So F has a pole, and a pole is just, it's the same idea as like with a rational function from algebra 2 or something, where it's You just have this asymptote that the function goes off to infinity or something near it, but never actually hits it. So it has a pole if there is a finite number, a positive finite number of the negative terms which are not zero. Right, so this is essentially says that you could write, so if you look at your function f, you can pretty much just write it as another function, g, divided by z minus z naught to, say, the m. So where m would be like the biggest number such that a sub negative m would be non-zero. Or yeah. So that, like, something like this obviously has a pole here if g is holomorphic. So that's essentially what it means. And then the third case is where there's an infinite number of negative terms which are non-zero, and that's called an essential singularity. And this is, we're not actually going to go into this because doesn't show up in the integral, but these are really weird, and there are only a few examples of them. Like the function e to the 1 over z has an essential singularity at z equals 0, but it's really weird. It actually comes up with some interesting theorems. Like, I would recommend Googling this, the Kazarati-Weierstrass theorem. It's very interesting, but we won't touch on those again. So if we move on now, so if you take a function that's holomorphic on this set U, take away the point z naught, and you have some Lorentz series for it, then suppose that f has a pole at z naught, as we talked about. Then you define the order of the pole as the greatest positive integer m, such that a sub negative m is equal to 0, which I've sort of talked about, right? So biggest m such that you can write this, and g is holomorphic on a disk. So it's essentially like how extreme the pole is, right? So this is an important notion that'll be important for calculating things in our integral. So we'll come back to it later. So now if we look at this, let u be an open set and let f be a meromorphic function. So meromorphic is just holomorphic, something that's holomorphic everywhere except for at a few isolated points. So points just sitting around. So if u is this, so f could be holomorphic on this set, or if it was meromorphic, then there might be little points where it's not defined, but there's not like a big blob of points where it's not defined, right? So it's just individual points where it's not defined. So usually those are removable singularities or poles or something, right? So suppose f is a meromorphic function, and it, say at z naught, it has a pole. Then the residue, the way you calculate the residue, is with this formula. So I'm assuming if you're watching this and have gotten this far in the video, then you know calculus and semi-enjoy it. So I'll actually let you figure out how this formula works. It's not super complicated, but I will say if the function has a removable singularity at z naught, then the residue is just 0. Because remember, if it's a removable singularity, then all of the negative terms are going to be 0, which means a sub negative 1 would be 0, and that's the residue. And meromorphic functions actually cannot have essential singularities, so it would have to be poles or removable singularities. So this formula will certainly come in useful later. All right, so that, if we touch back on this notion of residue that we talked about, then we've now touched on everything. Right, we understand what a residue is because we understand what Lorentz series are, and we understand roughly how you can calculate residues. There are a few other things to know, but this will be sufficient for the integral. All right. All right, so now that was part 1 of our introductory material. The second part actually has to do with integration. So the big theorem, which you may have heard of, is Cauchy's residue theorem. So let u be open, let gamma be a piecewise C1 cycle. That's a lot of stuff we'll come back to that is homologous to 0. I hate this term, actually, and I won't really define it, but I'll say roughly what it is. So it's homologous to 0 in U. So then let F be meromorphic on U with no poles on the image of gamma, which means like, well, gamma's essentially a bunch of little paths, right? So it might look like that or something. This just means that there's no poles directly on the curve itself. Might be a pole here, but there can't be one right on the line. So then the integral along gamma, which we'll define, of the function is then equal to 2 pi I times the sum of the winding number, which I actually will not really define rigorously because it won't be important for the integral, times the residue of the function at a point z naught. And this is summing over all the z naughts in U such that there's a pole there, or this essentially just means that it has a pole, and such that the winding number is not 0, which won't come in. I'll touch on that briefly. So first, this is probably the most important example in all of complex analysis, really. So let k be an integer and fix some z naught in complex numbers. So, and a radius bigger than r. Then we evaluate this line integral. So this is really just the same as Calc 3, the notion of a line integral. So when I write this, I mean that I'm integrating over a curve, which is essentially just the same as this. And this symbol just demonstrates the boundary. So this is really just a circle with radius r centered at z naught. So I'm doing a line integral along that of this z minus z naught to the k dz, where we traverse this counterclockwise, the circle counterclockwise. So it's like this, right? And then we're going to show that that integral is equal to 2 pi I if k is equal to -1 and 0 if k is not equal to -1. So you can already sort of see that obviously negative powers of -1 are important, because this says that z minus z naught to the -1 is important, whereas every other power is not, which connects obviously to residues, right? So we'll get into exactly how later. So the integral, we're actually calculating this. So what we first want to do is parametrize this circle, which the easiest way to do that is we do it like this, where we define gamma of t to be r e to the it plus z naught. And this just works because e to the it is actually just corresponding to the point on the unit circle with angle t, which is the basic algebraic foundation of complex analysis. And most people brush on it in pre-calculus. It's similar to what's called de Moivre's theorem, which says this is equal to cosine t plus I sine t. So the parametrization then is this just essentially brings the unit circle up to a circle with radius r, and this centers it at z naught. Right, so now we can integrate. If we want to integrate over gamma, then we do 0 to 2 pi of, well, we can do our substitution, right, where z is equal to r e to the it plus z naught, then dz, excuse me, is equal to I r e to the it dt, right, which is actually just I times z minus z naught, which is nice. So now we have z minus, so z again turns into this. So r e to the it plus z naught, but then we're going to subtract z naught again. So we'll just leave it like that. Times, this actually doesn't matter. We'll substitute this in, I r e to the it, right? dt. So we can rewrite this as did I make a typo somewhere? Oh, it might have been a typo. Hold on. All right, if you're watching this, just skip ahead until I figure out what I screwed up. Oh, okay. I just forgot the k here. So that's nice. So we can factor this out and it becomes I times r to the k plus 1 integral from 0 to 2 pi of e to the it times k plus 1, right? So this integral, because e to the I times 2 pi is equal to 1, which is also equal to e to the 0, right? And when we integrate this, we actually just get this, right? So if k is non-negative 1, then the exponent is just I times a constant times t. So plugging in that and plugging in that gives the same value. 0 of k is not equal to negative 1. So if it is equal to negative 1, then it just becomes the i's cancel. And this actually doesn't apply anymore, though, because then this becomes just I times the integral of 0 to 2 pi of e to the 0, which is just 1. So dt, which is 2 pi I. So there you go. So let's continue. We have this important value, and this will come up a lot. So if we keep going, let u be an open set, and let f be a holomorphic function on u, and pick some point in u and some radius, such that this ball, centered at 0 with radius r, is fully contained in u. Then we have these two properties. And these are actually not pertinent, but they're interesting tidbits of how complex analysis works. So the nth derivative of the function can actually be given in this integral expression by n factorial over 2 pi I times the integral around the boundary of this circle times f of c over c minus z to the n minus 1 dxc. And I obviously will not explain how you get this because it's very complicated, but this is a very cool formula and it's very useful. And then the second part is this means that you can bound the modulus of this by this value, because this is really just taking the modulus of this. That's where the n factorial comes from. And the way that you give an upper bound to an integral is you take the length of the curve that you're integrating over, which is 2 pi r. It's just a circle with radius r, times just however big the integrand can get, which involves biggest that can get and the smallest this can get. But this is actually, the modulus of this is always r, because z is at the center. Or no, sorry, what am I saying? The smallest you can get is r. So you get this r to the n plus 1 in the denominator. And you still have the n factorial over 2 pi I from before. And then supremum just means the biggest that f can get on this circle. So, and the I actually goes away when you take a modulus. So this becomes n factorial over r to the n times this supremum. So that's not super important, but it's interesting. right? So if we continue, now we get to the definition of a cycle. So a cycle is a formal sum of these loops, where this just means like each of these gammas is a loop, and a loop is just any sort of parametrized curve where the endpoint is equal to the starting point, right? So it's closed, right? And you learn that in Calc 3. So a cycle then is just a bunch of these thrown together, and a formal sum just means like you can just add the pictures together, and it's you sort of understand what you're talking about. So a cycle is piecewise C1 if each of these gammas is piecewise C1. So C1 just means the derivative is continuous, right? And piecewise C1 just means that the derivative is continuous except at finitely many points. So something like that would be C1, but something like, say, that would be piecewise C1, because the derivative is definitely continuous everywhere, but here the derivative actually isn't defined there, right? So it's C1 except for those few points. So, okay, that's what the piecewise C1 cycle is, so we'll come back to that. So if we continue, so let U be an open set again. And this is a very important idea. So let U be an open set, and we have two C1 loops. We say that they're homotopic if there exists this continuous function mapping both this interval and that interval. And this is the interval corresponding to these curves, or these loops, because notice we define both loops in the same interval. And this parameter 0 to 1, such that it has these properties. So h of s comma 0, so when the parameter is 0, we essentially just have gamma 0. So if you plug in 0 for the parameter, this spits out just gamma 0 as a curve. You get this different function. Similarly, if t is equal to 1, then you get gamma 1. And this third condition is saying that no matter where in the parameters you are, the endpoint is always equal to the start point if you think of it as a contour. So really what homotopy is if you have, say, one loop like that, one loop like that, all you're doing is slowly deforming them. So it might look something like this. Slowly maps to here. These are just increments of t for the function h, right? So you're deforming things. And notice the important thing is, say, if U looks like this, U might have a hole in it, like the U is the interior of here without the hole. Then a loop like that would not be homotopic to a loop like that, because you can't deform this to that continuously, because you would have to pass over this hole. And to pass over that hole, that means that values of the loop would have to be outside of the set U. So these would not be homotopic. And that comes up later in the integrals. So if U is open and you have these two homotopic loops, then the integrals of a function, holomorphic function, are the same over each of the loops. And that's precisely because they have the same sort of nature where if, say, there's a point inside the loop that's not in the set, then it's preserved between gamma 0 and gamma 1. And I won't prove this because it's very complicated. Deals with some other things that I didn't mention. But this also comes up, and I'll talk about that. And it's useful for this theorem, actually. So this is the simple version of the theorem we saw a little while ago. So suppose that F maps this annulus, which is just the disk without Z naught, right? Suppose F is holomorphic, and you have some new radius rho between 0 and r. Then the integral about the boundary of the ball of radius rho, so essentially just a circle of radius rho centered at Z naught, of f of z is equal to 2 pi I times the residue. So that has a very intuitive explanation. So the intermediate step is you can write it like right? And here you can just swap the order of the sum and the integral. This integral is 0, except for when n is equal to -1. All right, so this simplifies to just a -1 times 2 pi I, as we know that that integral is 2 pi I when we have that. So this is the residue. So you get that. These are the same. So this is where it starts getting cool. So now we have all of our components. And I will note, if we go back to the bigger version of the theorem, right, Cauchy's residue theorem, I defined what a cycle was, but we're actually not going to really need full cycles. We'll just need some piecewise C1 loops for our integral. And homologous to 0 is sort of what I was talking about with regards to this. This just means that if it's homologous to 0, then every point inside of the loop is also contained in U. So this would not be homologous to 0, but this would be, because like there are points in here that are not in U, but they're inside the loop. So this is saying this only holds as long as everything inside the loops is in the set. Right? And that's because we're defining F to be meromorphic, not holomorphic. Okay, so now before we get to the actual integral, we'll do a brief, much simpler example of how to apply all this. So take this integral. This is a real valued integral, but you would not see this in a calculus class because it's impossible to do with normal real valued methods. You have to use complex analysis. So the trick, let me refresh myself what the exact trick is. Again, just skip forward as I make myself look stupid by not knowing what I'm talking about. Oh, that's right. So what we do to make this very nice substitution, let z equal e to the I theta. Right? So the new boundary is now a loop, because when you take 0 to 2 pi for e to the I theta, as we talked about, that's just the unit circle. So you can write it like this. And this script d actually just represents the unit circle. So we'll leave it like that. 1 over. Now we need to figure out how to write all this. So dz is I e to the I theta d theta, which is just I z d theta. Right? And how do we write sine theta in terms of z? So there's a formula. Sine theta equals e to the I theta minus e to the negative I theta over 2i, which you learn just in regular complex analysis. So what we need to do is, well, we can write this as z minus 1 over z over 2i. Right? So this becomes, and I'll write the 2i up here actually, z minus 1 over z times this 1 over iz d z. Okay. So we can simplify this. We get 2 out front. And you can combine this. Or there's a plus 3, sorry. So it becomes 1 over z squared plus 3z minus 1, right? Actually, no, I made a mistake. Sorry, the 2i cannot go up the front because there's a 3 there. So forget that. We'll try that again. So this becomes, you can still combine these. So this, for example, would become 1/2 z squared. We have the 3 plus 3i z minus 1 which we'll actually now write as this. Right, so, okay, let's look at where the zeros are, because as we remember, if there are no poles inside of this loop, then the integral is 0, right? So essentially what we're doing is looking for the residues of this. So how do we do that? So we don't actually have to get into residues, which is convenient. We just have to find the poles. So if we say, and I'll clarify, that's because residues that are non-zero can only occur at places where you have poles. We're not going to have any essential singularities, as I already said. So the residues can only occur at poles. So that means that the integral is perfectly dependent on where the poles are. So let's factor this. And I mean, you can use quadratic formula. So -6i plus or minus the square root of -36 plus 4 right, over 2. And that becomes -3i plus or minus 2i root 2. So these are where the two poles are, right? So we have to check. Oh, did I make a mistake? No, that's correct. Yeah, so we have to check which of these is inside the disk and which is not. We can rewrite this as I times 2 root 2 minus 3. So, or plus or minus 3. So, okay, if it's plus, then 2 root 2 plus 3 times I is way too big to be inside the circle. Z in circles like that. 2 plus root 2 plus 2 root 2 plus 3i would be like way up here. So that doesn't matter. So 2 minus 3 root I would be in the circle because 2 root 2 the square root of 8, right? So it would be bigger than 2 and smaller than 4. So the difference is then somewhere in here. So it would actually be down here. 2 root 2 minus 3. So that matters, right? So all that we have to do then is show that this is equal to 2 times 2 pi I residue of z is equal to 2 root 2 minus 3i f of z. So how do we calculate that? Well, let's see if I can pull up the formula. I didn't lose it on many papers. Yeah, the formula is right here. So it's convenient when m is just equal to 1. This simplifies everything. So this, the formula turns into, I'll just write 4 pi I times, so when m is 1, this goes away, and this is just a first derivative, this is just a first power. So well, this is a 0th derivative, so you don't do a derivative. So it just becomes times the limit z goes to 2 root 2 minus 3i of z minus z naught. Z naught is 2 root 2 minus 3i to the first power times the function, right, which is 1 over z squared plus 6iz minus 1. But, I mean, we know that this factors into z minus the first root times z minus the second root. And this is the first root. So this just turns into 4 pi I times the limit, which I don't want to rewrite, of just 1 over z minus the other root, which is 2 root 2 plus 3i. And the limit doesn't even do anything, so you just plug in the value. So 4 pi I times, okay, you plug in 1 over 2 root 2 minus 3 I minus 2 root 2 plus 3 I. And this just, the denominator then just turns into negative 6i. So it's 4 pi I over negative 6i is negative 2 pi over 3. So that is an integral you could never do without a complex analysis, just wouldn't work. Right, so but we found an interesting number, right? Okay. Yeah. Excuse me, I actually made a mistake. The other root was not that. It should be negative, negative. So it's negative, negative. This is not 6i, it's 4 or 2i. The answer is actually pi over root 2, or you can rationalize that if you want. I don't care. Yeah, okay, that's better. Yeah. So we've now introduced the process. So now we can jump to this interval, which gets way harder. So problem is, the hardest thing actually is coming up with the substitution. So this integral was problem 5 on our homework 9. And I spent probably about 12 hours trying to figure it out, 9 of which was just guessing different substitutions and different contours. Because really it's not about the substitution, it's about just drawing stuff and hoping that it works. So I tried lots of different things, and I won't go through all the things I tried because I don't remember them. I didn't keep that scratch work because it was painful. But when I finally found it, I was very excited. So here is what the contour is. And actually, we won't do the, yeah, we will do the negative case first. Why not? And I won't even tell you how I came up with this because I don't really know. So I'll actually, okay, we'll consider that this is R instead of, let's wave that. Excuse me, we still have the e to the negative 2 pi I x c dx. But c is a negative number, so this will actually end up being a positive numerator times x. So the contour that good old Tristan came up with is this. Because all we're really going to do is calculate this in terms of r, then take a limit, because you don't, like, there's just no other way to do that. So where this point is r, this is negative r, this is r plus I root r, this is negative r plus I root r. I know it's really weird. So what we're going to do is apply Cauchy integral theorem to the integral with forgetting about the limit for now, right? So the way you can do that is just to break it up into integrals over the 4 sections. So first, we're going to calculate it with Cauchy integral theorem, then we're going to calculate it explicitly. So with Cauchy integral theorem, we just have to find the two, they're the poles. So the poles of this are just at I and negative I, because this factors into x plus I squared, x minus I squared. So because this is just an elementary looking function, it has poles of order 2 at I and at negative I. And the only one of those that occurs in here, because we actually only care about the limit after R is bigger than 1, which is a perfectly valid thing to do because you only care about end behavior. The only one that occurs there is I. So for this, the integral is equal to just 2 pi I times the residue at I. of the function. Or z, I guess. So we're going to treat this as if it's a complex valued function. Or we're not actually going to look at this. We're going to treat it as if it is a complex valued function. And we're going to call this gamma sub r, because it depends on. So the integral of f of z, or f of z, right, is just z cubed over z squared plus 1 squared e to the negative 2 pi I z c. So that's fine. So this is just Cauchy integral theorem, or Cauchy residue theorem, sorry. So we need to calculate what that is, obviously. So we saw that it was a pole of order 2, just because of that and because of algebra 2 knowledge. So if we again apply formula, which recall was this, now m is equal to 2. So this will just be a 1, this will be a first derivative, and this will be a 2. So what does that turn into? 1 z goes to I, d over d to z. And I'll say, like, derivatives for complex functions are, you calculate them the exact same way. You use the same rules, chain rule, product rule, whatever. So this would just become z cubed over z plus I squared e to the negative 2 pi I z c. Right? So this becomes, here is actually extremely annoying, so I'll just tell you what it turns out to be. I'm not even going to write what the function turns out to be, but this is, you can do this as an exercise, because you have all the tools to be able to do that. So the limit turns into 1/2 e to the 2 pi c times pi c plus 1. Just weird and disgusting, but that's fine. So that's equal to, the 2's cancel out, so it's pi I e to the 2 pi c pi c plus 1. Right. So this is not the answer. This is the integral over this whole thing. So what we're going to do is calculate the integral over that, plus integral of that, plus integral of that, plus integral of that. We're going to subtract these 3 from the whole thing. We'll be left with this. Right? Because all 4 components, if you subtract 3 components, you're left with the last component. So we need to calculate those. So we have to do 3 explicit integrals, right, and subtract them from this. So the first integral, we'll start with this leg. And again, we'll just deal with the complex valued function, but we actually have to parametrize it. So the I'll just show you how I would do it. So you go from 0 to root r. So the parametrization is going to be gamma of t equals r plus it. Right, so start at 0, we get down here, start at root r, end at root r, we get up here. So we just plug this into f. It's line integral. Y prime is just I, so it's fine. My integral of plugging that in is really annoying. So let's see, it becomes 0 to r plus it cubed over r plus 1 plus it squared e to the negative 2 pi I r plus it C, D, D. So that's nice. So how do we integrate that, you ask? Well, that's a good question. So to do that, we actually don't do that. So I actually lied to you before. So what we're going to show is that this integral goes to 0 as r goes to infinity. Because all we need to show is that this integral goes to something. So we're essentially going to prove it's equal to this. Because if we call this integral I1, call this integral I2, call this integral I3, then we know that our actual integral that we care about, call it just I, right? I is equal to this number minus I1 minus I2 minus I3. So if we take a limit as r goes to infinity of both sides, if all of these go to 0, then it's just that. Because that doesn't depend on r, right? So we just need to show that the limit of this integral as r goes to infinity is 0. So how do we do that? This is actually why I commented a long time ago on how this works. So what we're going to do is show that it's a really long thing. We're going to show that, right? So we break this down. As I said, you can chalk this up to this is equal to the length limit is r goes to infinity of the length of the integral, which is just root r 0 to root r. The I goes away because it has modulus 1 times then the biggest the numerator can get and the smallest the denominator can get, because you're trying to find the absolute maximum of the whole integrand. Well, there should be a dt. Sorry, someone got to catch me on that. Because if you take the absolute maximum, you actually have a less than or equal to here. And if we show that this is equal to 0, then that's equal to 0 because it's positive. Or it's non-negative, sorry. So the biggest the numerator can get as a function of t, right, is just r plus I root r cubed. The smallest the denominator can get is just r plus 1 squared, right? And then this exponential, what's the biggest that it can get? Well, let's break it up in two. So this e to the negative 2 pi I r c is fixed. And then we're left with e to the negative 2 pi I times I, which actually cancels out the negative. So it's 2 pi times t times c. The biggest that can get is actually when t is the smallest, because remember, c is negative. This is why it matters. So this becomes looking at e to the 2 pi t c. To maximize this, we want to maximize that. But this is always negative because t is never negative, but c is always negative. So the biggest that can get is just 0, right? So it just turns into 1 so that we don't even do anything else. So if we take this limit, this is actually extremely easy to do because you have, or sorry, what was I just thinking about? Just to clarify that I'm not doing something wrong. Yes, so, sorry, I didn't even I made a mistake here. When there's an I, the modulus is always 1, because modulus of this is just 1. So this actually goes away. Sorry. So this is easy to do because we can look at the degrees of everything. Right, so what's the degree of the numerator? It's ends up, well, okay. We don't have to actually expand it out, but the biggest this part gets is to the 3. So then you multiply by root r, it goes to the 3/2. But the denominator gets to the power of 4. So if the denominator is a bigger power than the numerator, then it just goes to 0. So it's 0. So it's fine. So we did that. So what we would then do is the same idea for that and for that. And that ends up working. I'm actually not going to write it out. But the reason you have to pick this very particular shape, the reason it has to be r and root r, I'll show you. It's related to this. So suppose it was just r plus ir. That would seem like the reasonable thing to guess, or at least more reasonable than this, right? Then that would be r, and that would be r. But then the numerator here would have power degree 4. And the denominator would also have degree 4, so it wouldn't necessarily go to 0. Right? So that you need something that has power less than 1. So it could be r to the 2/3, it could be r to the 1/millionth. So it doesn't actually make a difference. But I chose root r, and this works. Right? Yeah, okay. So again, I won't, well, I'll write out what the integral setup for I2 would be. Right, it would just be integral from, and the way you parameterize this is starting here going to here. So this is the thing changing the real part. So it goes from r to negative r of f of gamma t, gamma prime of t dt, where gamma t is actually just t plus I root r. So this part is actually not too bad, writing this out, writing what this is. Then you just plug this in, and it actually looks a lot like this. And it'll end up going to 0 if you do the same process. Similarly, I3, which really looks pretty much the exact same as this, also goes to 0. So that tells us, right, that the integral then is just that number as I explained. So now we need to do the final case where c is positive. So we'll flip this over. So if c is positive, then we switch up the contour or the loop we're using. Now we want it to be on the bottom. And we always want it going counterclockwise, because I didn't talk about winding number, but for the winding number to be 1 and not impact anything, not to touch the integrals, then you want everything going counterclockwise. So this is the same sort of shape. This is r, negative r, r minus I root r, negative r minus I root r, right? So if we're now looking at c is positive, then it's still, we're still looking at this function, obviously. So if we integrate that, then all we care about is whatever residue is inside here. And we know that the residues only are non-zero at the poles, and the poles occur at plus or minus I. Negative I is right here. So the integral, we'll call this gamma r again. Gamma r f of z dz is just 2 pi I times the residue at z equals negative I of f of z. All right, so this is again degree 2 residue. All right, so it would look like this, which I will not actually write out the calculations for because it's horrifying again, but you end up getting, let me make sure I get this right, negative pi I e to negative 2 pi c pi c minus 1, which is a lot like the number we had before. Right, the only real difference is that there's a negative here, which doesn't make a difference because c was positive, now it's negative. So it's actually this exact same value if you take absolute values of c, right? Because there's a negative thrown up in the exponent, and there's a negative thrown up front. But that cancels with this negative if you multiply that by -1. So it's really the same number, which makes sense. So we have that. And we want to do the exact same process, showing that we call this I, call this I3, I2, I1. We want to show that I1, I2, and I3 all go to 0 as R goes to infinity, and we'll get the exact same result. So this is our conjectured answer, which, spoiler, it actually is correct. But let's try this for I1 just to do it. So I1, we know how to parameterize that, right? So it goes from 0 to negative R of f of z, no, f of gamma of t times gamma prime of t dt, where gamma of t is equal to negative R plus it, right? So this is equal to limit. So R goes to infinity. This disgusting thing, negative R plus it cubed over negative R plus it squared plus 1 squared e to the negative 2 pi I negative R plus it times c, then times derivative of gamma is just I. So I'll just throw an I out here, dt. So again, we do the process. It's less than or equal to the biggest we can make this. So we get this root R as the length of the bounds. The I goes away. This will go away because it has modulus 1, which is just a basic complex analysis fact. And then this ratio here. The biggest that the numerator can get is when you have t equals root R. So negative R minus I root R modulus, sorry. Smallest the bottom can get is when t is equal to 0. So negative plus 1 squared. And again, the numerator is a cubic plus the square root, so it's to the 3.5 power. Yeah, I said 3.5, 3 halves earlier, but it should have been 7 halves. So 7 halves power in the numerator and power 4, which should be squared, power 4 in the denominator. So it again goes to 0. And similarly, I2 and I3 will go to 0. So it ends up being this. So you have the beautiful result. And this you can like write down. I've abused this a lot. So what I actually did when I was in the chemistry building for some odd reason, when I finally solved this, so I spent like 2 days on it, and it was like 9 p.m. the second day when I finally got it. I probably cried, I don't remember. And I wrote this result on a blackboard just in one of the common areas. And I felt really good about myself, actually. But just to flex some of the chem nerds, right? C is positive. Remember, at 0, C is negative, which doesn't even require complex analysis. And then it was this very similar Okay, so there you go. That is the answer to probably the most difficult integral I've ever done in my life, and probably the most difficult integral you will ever encounter. So yeah, hope you enjoyed